Hello, everyone. Yeah, welcome to back. Let's wait for another several minutes because there is only about 20 to 25 students here. So let's wait for another minute and we can start our lecture today, online lecture. Yeah, so maybe we should start. Okay, so let's start. Today, let's finish the OpenMP chapter, and I will give you two examples in the end about demonstration. I will do the running the code and benchmark the performance for you, and after that, I think you will have idea how we can program OpenMP code and how to test the performance, and what's the difference between the OpenMP code and MPI code. Okay, so after this week, I will give another project for how to use OpenMP to program a product code, okay? And next week, we will start with GPU programming. So I think until the end of this month, we still have about 3 weeks, we can get some idea how we can program a GPU code, okay? After that, I will give a final project, and I think that's it for this semester. We don't have any final exam, but I will give about for the OpenMP project, Cuda project, and I will give the final exam as a take-home assignments for another project. Okay, so I think that's it for this semester schedule or arrangement. So if you have any question, just let me know. So today I think I will finish the OpenMP chapter. I will show you two examples how we can run OpenMP code for a real problem. So I think the last lecture we have discussed and I have introduced the OpenMP programming. Still remember, we have some program, mostly OpenMP supported from the compiler. So the compiler will, based on what you code in as a directives, right, or programas in the code, and then transfer your code into multi-threading mode and give you some performance improvement. Okay, that's the general idea of the OpenMP. It's a compiler-assisted technology, okay? So you have to have the compiler support. You just put some pragma and directive there. Okay, that's the idea. So, okay, let's see the first example, how we can calculate pi using OpenMP code. So the general idea is that how we can approximate the value of pi using a loop, okay, using a finite number of steps, okay? So because the pi is a floating point number, right? So you cannot get exactly the number, but you can approximate the value of pi using some formulas. So here is a mathematical proof of how we can get a value of pi from the numerical integration. Okay, so some of you may still remember how to do the mathematical integration from your calculus class, right? So if we want to get the approximation value of pi, we should start from the numerical integration formula here, okay? So we can approximate the integrals as a sum of the rectangles. So I think this is the basic idea in your calculus. So you want to approximate a value of the integrals using the finite number of steps, right? So you should do a summation of some formula, and when the n trends to the infinity, you will get the integrals, right? You will get the integration. So that's the general idea. So how we can use a program to calculate pi? Maybe in some class you have already know that, but let's just to recall how we can get a value of pi based on some for loop. Okay, so the idea is that how we can calculate the value in the left, and when we use a larger and larger n, our value would be approaching the value of pi, right? That's the general idea. So how to calculate the left-hand side the value? So we need to use the height fxi at the middle point of the interval, and then we need to times the delta x here. Okay, so fxi, f is a function for the 1 divided by 1 plus x squared. Okay, so this is function is f, and delta x is the interval size. Okay, so after we have the summation result, we just use a different number of the n, and we can approximate the value of pi. So here is a mathematical explanation. Okay, then the next step is how we can program simple code to calculate the pi. And then we will from sequential code to go to the parallel code using the OpenMP. Okay, so that's the general idea. And here is a sequential code. So it's I mean, if we have a number of the steps here, we define as this is a 10,000. Okay, this is a 10,000. We can use an even larger number, but larger number means you need to have more computations and more times here, but you can get a more accurate the value of pi, approximate value of pi, right? And each time we just use this x means the middle point of the interval, right? I minus 0.5 times step size. And then you will put the x into the function f, and you add the value into the sum function. Okay, you want to calculate the sum. So after that, you will divide by the number of steps, you will print the approximate value of pi. So here is the sequential code. Okay, I don't think this is difficult for you. This is just a simple loop to calculate the value of the pi. Okay, so maybe we can quickly run the sequential code to see if I can get some results close to pi. So I prepare a code here. So we have the pi. Okay, this is the sequential code. This is the sequential code. I think it's exactly the same as the code in the slides, right? I just copy and paste. I don't change anything. Okay, so here is the code. So let's try if we can run the code. Okay, so this is a sequential code, remember? So this is sequential code. So if we use a 10,000, we will get the value of 3.1415926535598. Okay, so if we change the different value of step, how many steps? For example, I will add 20 here. That's 10 million, right? 10 million steps. So it will get a different number with this one, right? I think this one should be closer to the real value of pi because I only print some digit after the, I only print several decimals here, right? So, but I think this value is closer to the real value of pi. Okay, but you take more time because CPU now is very fast. Even I add 20 into the number of steps, maybe you cannot sense. But if you add a timer, you will see the difference. Okay, but this code gives us an idea how we can get the value of pi. Okay, but this is a sequential code. The idea is that we can simply add some pragma to the loop to make this code running with multiple threads, right? So that's the idea. But how can we add the pragma or directive here to use the OpenMP supports? Okay, that's the idea. So let's see how we can make a parallel OpenMP code. So we have several different strategies. So here is the first version. So I will show the second version. Okay, so here is the first version. The first version is very straightforward. Is we just add some pragma OMP parallel. I still remember this pragma. And this is something we denote which variable is private, which variable is public, right? So here we just add a pragma OpenMP parallel. So in this region, all the thread would execute the same thing, right? Same code. But similar to MPI, you have to let different threads know which iteration they should execute. Okay, so here you can see that this is exactly similar to MPI. So for ID, you can think about the MPI rank here, right? And each process here is each thread. Each thread would process the iteration every number of threads. Oh, sorry, I should change to the slides. Sorry about that. I don't. Okay, so here it is. Okay, so maybe yeah, I should repeat that. So here I add some pragma to the loop. Okay, and for each loop or for each thread, the thing you need to pay attention is that which thread would execute which iterations, right? It's exactly similar to MPI code, right? So ID is the rank ID, right? Here is the thread ID. And then we will, for each thread, we will ask the thread to execute every number of threads iteration. So for example, here, for the thread ID 0, maybe I should use a larger. I'm not sure if you can. Anyway, maybe it's a little bit small, but yeah, so let me just quickly write something here. So ID 0, for example, now we have the 4 threads, right? So for the ID 0 or the thread 0, it will execute the iteration 0, right? And every time it increases by the number of threads, it's 4. So it will include 0, 4, 8, 12, 16, 20, right? Until 10,000. 10,000 or 100,000. It should be 100,000, right? 100,000. Okay, so here. And then the ID thread 1 will execute 0, 5, 9, 13, 17, 21, right? So I think you have some idea about this because you have already learned how to program MPI code. But here you need to manually set which thread need to execute which iteration, okay? And finally, you will get all the sum results together and use the sum result to divide by number of steps to calculate pi. Because for sum, you need to have the different intermediate sum result, right? So after you get this summation, you will put the value into the sum 0, right? And after that, you will put this into the sum 1, okay? So if you have the thread 2, it would be until put the sum of this iteration into the 2, right? And after that, for example, we will have the 4th thread. So totally we will have sum 0, sum 1, sum 2, sum 3, right? And then you will add all the result together, okay? To get the final summation. So that's the idea of this code. You have to manually set up something, right? So set up which thread would execute which iteration, and you will get the intermediate summation result, and you will finally put the intermediate summation result into the final one, right? But some student may also, may intermediately think about the reduction operation. So then I will give the second version. But now let's first focus on this version. Okay, let's do some benchmark and run if this version can give you the correct result. Okay, so let's show you the results of this one. So here I have another code. It's OMP pi. Oh, yeah. Yeah, it's OMP pi. So exactly the same as the code in the slides, but I increase number of the iterations or steps here. So it's 1,000, 1 million, it's 100 million. Okay, because I want to test the performance improvement, right? So here, let's first test with 4 threads. Okay, or maybe 2 threads. So here I also, put a timer here. So I will give an explanation of how you can use timer, but it's just like an MPI get time, war time, right? It's very simple. And it gets the execution time or war time from each thread, okay? So you can count the execution time here. So let's quickly compile this code and execute this code. So it takes some time. You can see it takes about 1.5 seconds, and give you the results of pi. Okay, but if I change the number of threads, can I increase the performance or can I reduce the execution time? For example, I increase 2 here to 4. Okay, I just recompile. I just re-execute. Oh, the performance is not good. Okay, let's continue increase the number of threads here. If I increase to 8. So that's why sometimes I say that the OpenMP cannot guarantee the performance to be always increased. But let's first see if 4. Okay, 4, you can increase the performance. Let me try. Sorry, 8, we can increase the performance. Let's retry 4. Okay, 4 is not good. But 8, you can definitely reduce the execution time. Maybe because of never head node, and some people are running the code, right? So maybe let's just SH to a computer node. Computer node, okay. So what about GPU 01? And maybe I can execute in the GPU node. So let's retry, okay? So okay. Because the head node, sometimes people are running the other job using the head node. Let's just use the compute node. So let's first try the 2 threads. One 94 seconds. If I change the number of threads to 4, slightly reduced, right? But it's not too much. Let's try to increase the threads to 8. Okay, you reduce the time from 1.94 to 1.85 to 1.35. Let's use 16 threads. Okay, it's reduced to almost half second. Let's try to use 32 threads, because in this computing node, we have the 32 threads. We have 32 cores, right? So let's try to use the full of the threads here. Okay, so you can see, even if you are using the 32, the performance will not be reduced, right? So let's just try to write all the results in the slides. So after, for example, now you have the two threads, you will have the execution time of 1.94, 4 threads, 1.85, 8 threads, you have time of 1.35, 16 threads. Okay, so that's the result we get from the computing node. Okay, so that's the reason I'm saying that sometimes you shouldn't execute the code on the login node, because login nodes need to manage the whole system, and some people may run the job, so it will affect your result. Okay, so if we use a computing node, we will get something right, makes sense or reasonable. The problem you can see here is the number of the threads. Even if you double, the performance is not exactly reduced by half, right? It's not like an MPI. You can maybe sense some perfect speed up, but for OpenMP, just as mentioned, we cannot guarantee the performance or speed up improvement, because if you want to switch the thread, you also need to pay some performance overhead, right? But the general idea is that we can increase the number of threads to improve the performance. For example, from the almost 2 seconds to almost a half second. So that means we increase the performance. Maybe I should test this one thread, right? Maybe I should quickly test one thread. Give me 1 second. Let me quickly test one thread so that we can know the speed up or power efficiency. Let me. I don't want to switch the screen sharing. Let me just quickly test. Okay, here's an interesting thing. So if I use one thread, the performance is even better than the 2 threads. So here is the result I get from the node. Okay, so here is some explanation, right? Because if you use 2 threads, maybe for each thread, your computation task is not very large, right? But you need to pay some overhead to manage the 2 threads here. So that's why last lecture we mentioned that even for 2 threads, we may observe some normalized speed up lower than 1, right? So here, if you normalize the performance based on the 1 thread, you will observe some speed up lower than 1, right? So here is some result you can get from this code. I will show another code. Another code I believe should have a better parallel efficiency than this code. So for this code, you can see the performance parallel efficiency is not very good. You from 1 thread, but your performance is reduced, and then you improve the performance, you improve the performance, you improve the performance, but you cannot improve the performance by using the 32 thread, right? So here is an example, and I just want to show you something. The OpenMP may not just like MPI, that regular, right? For MPI, use 2 processes, 4 processes, or 8 processes, you can definitely get some performance improvement. But for this one, it's not guaranteed, okay? Then let's see second version. Second version, so some students may think about, okay, why we need to manually set up which thread to use which iteration, or to calculate which iteration, right? Can we use a reduction? Yes, we can use a reduction. So here is a recall for OpenMP reduction. This is just a quick example that you shouldn't use a reduction like this way, because if you want to reduction, you want to, okay, so here is the case. You shouldn't set a primate variable for the sum, because if you set a primate variable to the sum, and there would be a bug, because sum would protect it by each thread, and each thread will have its own sum, right? And if you use the private sum, then you will not get the overall summation, and you cannot get the average, right? There would be a bug here. So the problem is that we really need to sum all the threads together, right? And the reduction, as I mentioned before, can give you this capability to reduce or perform the summation for all the threads, right? So I have mentioned in the last lecture. And for the reduction, so the first is operation, and second is the variable you want to put to the reduction result. Okay, so I think we have already learned the reduction operation in last lecture, right? I have already shown you a demonstration for the reduction, and this reduction can give you the sum over all the threads. Okay. So the second version is that, can we change the manual summation? Because, for example, we set the number of threads to 4, and we divide the iteration into 4 and ask each thread to execute some specific thread iterations. And then we calculate the partial or intermediate summation, and we add all the summation together, right? So that's the general idea. But if we use a reduction, the idea is that we don't need to let the thread know which iteration you need to execute, right? Reduction can help you to allocate or distribute the different iteration to different threads. So here is the code. I think the code looks much easier than the first version, right? You don't need to specify which thread to execute which iteration, and you don't need to have the partial or intermediate summation, right? You just add all the summation result into this variable. Okay, you only need to protect is a private variable x, because x is owned by each process. This should be totally different, right? You shouldn't use the x as a public variable. So x is a private variable, and you just put the pragma OMP parallel for reduction and specify the x as a private variable. Okay, and then you will get a summation result. So I will quickly show you the code and the execution result. But the idea, you will see that the reduction operation we adopt here can have better performance than first version, because the reduction implementation is better than what you implement the reduction, right? Here I can say that this is your personal implementation of the reduction, right? So this is the reduction implementation by the OpenMP. Okay, so let me show the code. Okay, so we have the OMP pi reduction here. Okay, it's the code I copy paste from the slides. We just use the reduction operation here, and we don't get the partial summation. We just get the overall sum here, and then we use the summation divided by number of steps to get the pi. Okay, so let's test if this one may be better than the first one. Okay, just make it clear. And then if I just execute this one. Okay. Whoa, it's only 0.3 seconds. So if I change it from the I change number of threads from 1. Let's test from 1, okay? This time let's test from 1. So okay, so for one thread, it's 1.2 seconds. Okay, if I change to 2 thread, it's 0.6 seconds. You can see it's almost reduced by half, right? It's almost reduced by half. Let's try to increase the number of threads to 4. Oh, it's reduced another half, right? It's 2.3. Let's try to see 8. Maybe I should close the window. There's gonna be a noise. Okay, so if I reduce the number of threads, increase the number of threads to 8, let's see the result. Have I changed? Okay. It's 8.
You already ran it once.
I haven't increased. I should increase to 16, right?
Yeah.
Okay. So sorry, I forgot that. Okay, so I have already executed 8. Let's try 16. Okay, 16, you almost, not almost, you exactly reduced to half. Well, let's try 32, right? So it looks like this code is very good because you use the reduction operation provided by OpenMP. So that's why I say the first code may not be the machine problem, may not be the system problem, maybe because of your code problem, right? Let's try 32, okay? Then let's count the results. Okay, this reduce again. So that's the perfect speed up, right? So let's change, put all the results into the slides, and maybe that's much easier for you to see the overall results. For this one, the thread 1, if we use the one thread, we will have, I just move the data from the screen to the slides, okay? So it's 1 second, and 2 threads, this one, 4, 8, 16, 32. Okay, so you can almost observe. So what's the speed up of this one? The speed up, not parallel efficiency. First, let's calculate speed up. The speed up is 1.8 divided by 0.959. Okay, calculate. It's it's exactly 2, right? Is exactly 2. Maybe I should get some more accurate timer, but yeah, this is exactly 2. But what about this one, the speed up? It's this divided by 0.3, right? 3.9. Yeah, it's 3.93. Okay, so you can get other speed up. But if you look at the final speed up, it's 29.5. It's a very good speed up, right? So you can also calculate the parallel efficiency. Do you remember how to calculate the parallel efficiency? It's equal to divided by 32, right? It's almost 92% of the parallel efficiency. So that means this code speed up perfectly, I can say, right? Perfectly. Almost you can increase the number of threads and you can perfectly reduce the number of you can reduce the execution time and you can maintain a very high parallel efficiency until the end, right? We only have 32. Okay, maybe that's a good idea to demonstrate if I use 64 or 128, right? So let's try this. Some student may curious, okay, can I ever increase the number of threads to ever increase the performance? So let's try, okay? So maybe I just increase the number of the threads. Oops, looks like networking is not very stable. Okay, so if I keep increasing the number of threads to 64, what's the result? Looks like the networking is not very good. Anyway, it's 0.05. You still remember the 32 is a 0.04, right? That means the performance increase. So let's try 128. Oh, it's still same thing. Okay, so if you take the CPU information, you can see how many CPU cores here? It's 40, right? So based on your previous experience on the machine, you can execute 32 processes in the same node, but you cannot execute it 64, right? Because you don't have such number of the physical cores. So let's explain why, okay, let's go back to slides. Let's explain why we increase the number of the threads from the 32 to 46. The time will not be reduced, but increased, right? So, okay, so here is this demonstration, I think is a very good example, give you some idea. So first, let me try to summarize. So first, we have the two exactly the same function, no purpose code, right? They just give you the same result. They just give you the same idea how to parallel the code using an OpenMP, but using a different method. The first one, you just manually parallel using the OMP parallel, right? But you have to specify which thread execute which iteration. The second version is that you are using the parallel reduction, right? You just change for another function. But after that, maybe I should copy this into this one, right? Belong to this side. Okay, yeah. So this is the version 2, right? So this is the version 1. We get some results here. We get some results here. Okay, so if you compare these two versions, right, you will definitely see that first, the OpenMP cannot guarantee the performance improvement for some code if your code is not optimized very good, right? So for this code, I can see your optimize is not bad. You just do what you can do, but because of the reduction operation implemented by the OpenMP should have some further optimization, right? We don't know what kind of the optimization. I don't know, you don't know, but we can ensure that OpenMP should have some optimization, right? Because it's a production level code, so that will give you some optimization. And then you will see that for the not very highly optimized code, the performance improvement will not be guaranteed by OpenMP, right? Even, for example, from 1 thread to 2 threads, the performance is just decreased. And while you increase the number of threads, the performance improved, and you cannot fully utilize the 32 thread. But for this case, we can fully utilize the results until 32, but for 64, we cannot, right? But for this case, we cannot even improve the performance after 16 threads. Okay, so I will give you a project to ask you implement something. And if in your implementation, you observe, okay, after 16 thread cannot increase something, maybe your code it's not further, not highly optimized, or maybe that's what the best optimization you can do, right? You shouldn't be too surprised why I have 32 threads, but I can only improve the performance to 16 or maybe 15, right? So that's the idea of the demonstration. So I think this is a very good example to show. Okay, so any question before I go into next example or next question? So any question regarding this one? Okay, so if you have any question, we can discuss similar to last lecture. We can discuss in the end. But this is the general idea how we can use OpenMP parallel reduction, right? They will give you better performance, better efficiency, better speed up than your naive implementation. Okay, so that's the idea. Next example, before next example, I have already put this timing into our code, right? So similar to MPI get award time, this is OpenMP get award time, right? It will return elapsed award time in seconds. So sometimes you can see I use the 64 and 128, only give me the same time because maybe the time is not very accurate, or I only print 2 decimals here, right? So sometimes it will not give you very accurate, but it should be fine for you because second sometimes it's good, okay? And the time is measured per thread. No guarantee can be made that 2 distinct threads measure the same time. Okay, so it measures per thread, and you just print one thread time here, okay? And the time is measured from some time in the past, so subtract result. That's the trivial thing. Every time you use the MPI get what time is the same. Okay, so this is OpenMP timing. So the next example is a parallel matrix application. I think this is much easier than the MPI matrix of application because you don't need to do any communication. You don't need to do any decomposition from row-wise or column-wise or block-wise. It's just put some pragma to the triple loop, okay? And I think we have mentioned the matrix application for many times, right, in the HPC class. And this is just a triple loops, okay? It's I, J, K, right? And if we focus on the inner 2 loops, this is outer loop, this is the inner loops, right? So inner loop will perform one row times another matrix, right? So this one row times another matrix would get the first row of the C, right? And then you will use another row to multiply this matrix, you will get the result of another row, right? So because this is 2 by 2 matrix, right? We only have 2 rows. So we separate the execution procedure based on the outer loop, right? And the straightforward idea is that we just divide the outer loop iterations with different threads here. Okay, so I think the idea is trivial. So you have just add pragma into the outer loop, right? And each outer loop will separate the iterations to n threads here. But here you need to think about which variable is private, which variable is public, right? So this is a good question to think about. So everyone knows how to write this part, right? This is definitely the trivial thing. But how we can make sure the private variable you write here is correct? So think about which things you want to only use by each thread. So for example, here, I divide the outer loop into the different threads, right? So for example, each thread want to hold some result by themselves. Which kind of the result they want to hold? So they just want to hold the temporary or intermediate result for each element, because this element needs to accumulate all the summations together, right? And after the inner loop, you need to put or write the temporary result back to C, back to the final matrix, right? So that means this temp variable needs to be private, because different threads need to have the different temporary result, right? What is shared? Definitely I is shared, right? I is shared because I is fixed in the inner loop. And I and JK is private because JK for different thread, JK is definitely different, right? I is definitely public because in the inner loop, the I is the same thing for everyone. Okay, so I think compared to parallel matrix and vector multiplication or matrix multiplication implemented by MPI, this code is much easier. You don't need to do too much things. You just put a pragma here, and the compiler will help you to automatically offload the different iterations into the different threads. And finally, you just need to copy all the temporary results back to C. That's it. Okay. So, but the problem, as I mentioned, so this example or the code implemented by the OpenMP cannot guarantee the performance, right? I don't want to show this how to execute and how to benchmark this result. Maybe you should do that. Okay. So maybe you can quickly put a pragma in your previous code. Matrix multiplication code, because everyone has the matrix multiplication code, right? Our project one is the simple is the how to optimize the matrix multiplication using registers and cache, right? So can you maybe try quickly to put this pragma into your code, and similar to what I just did to the pi calculation code, you can benchmark different number of threads, right? And see if the performance can be improved. But if you are using MPI, I can say mostly you will get a very good performance improvement. But I don't know. I don't know for matrix application. Based on my experience, it would not be perfectly speed up or scaled up. Okay, but maybe you can try. Okay, so this is case for our second. This is a second example. Okay, so a second example, I don't want to spend too much time because this is a really simple example, and you can benchmark by yourself. Okay, so here is the case, and I don't want to talk too much about OpenMP. I think that's enough for you to make a simple program and to mix the MPI with OpenMP. That should be enough. And based on my experience, no student want to write a p-thread programming. Even I have some slides here, right? How to demonstrate how to use a p-thread, but I don't think most of students want to use the p-thread because OpenMP is much easier for you to program. But general idea is similar. P-thread can give you some code begin and code end, join and fork, and some control of the thread, right? Similar idea, but it will give you some more flexibility to control that. So I hide these slides because I don't want to mention that too much. So that's it for the OpenMP. Okay, I think that's it for OpenMP. And I can quickly show you the OpenMP project, what we need to do for the next project. Hold on a second. Let me. Okay, so here's the next project. Okay, so I will adapt the time accordingly. And the first case is matrix application. Okay, because I don't demonstrate it in the class, so that's the thing you need to do. Okay, so how can you execute the OpenMP matrix application, right? I almost give all the code here. You just run the code and answer some question. Okay, you can add the necessary pragma, you can remove some pragma. Okay, I think that should be very straightforward, right? 1 thread, 4 threads, 8 threads, 16 threads, 20, 32 threads. Okay, on the computing node of Pentaheat cluster, right? Remember, you shouldn't run on the logging node. Okay, so this is the first question. This is the trivial to me. The second is the heat distribution. So heat distribution is a stencil computation I mentioned in last lecture, right? So you have some time step, right? For example, you from second 0 to 1 second to second to 3 seconds to 4 seconds. Different time step will give you the different structure of the array, right? The value of the array will change. And in each time step, you need to calculate all the points value. The idea is that I just give some temperature to some point, right? The temperature, the heat will propagate in the material or in the space or in the spatial area, whatever you want to say, right? Then I want to know after some second, after some time, I want to know which, maybe for example, this point, right? I want to ask what's the temperature of this point. And the temperature propagation follows some physical formulation, right? So here I think we just assume it's the average temperature of the neighboring 4 points, right? You will have each point you will have 4 neighboring points, right? I minus 1j, I plus 1j, I j minus 1, I j plus 1, right? So you just use this formula to calculate. And I almost give you the code, right? You just try to use the pragma, use OpenMP to parallel this code, right? So this is the time, right? And this is the spatial, okay? There are 2 parts of this code. The 3 problem is just to ask you to calculate something or ask your code to compare with sequential code, okay, to verify the correctness. Second, what is the second part? Second part is just ask you to test your program with some specific n and t. T is the number of the time step, right? N is the space size, right? How many points we have. Okay, so this is project 5 using the OpenMP to cover matrix of multiplication and to cover heat distribution. Heat distribution is a stencil computation, okay? And the first case is what I just discussed. It's very easy or trivial to just put some pragma into the outer loop, okay? So that's it for the OpenMP section. OpenMP is very useful and give you some improvement using multi-threading, but because it's still shared memory, right? So you don't know how much performance you can gain from the different number of threads. Maybe sometimes you can gain very good, sometimes not good, but mixed with MPI, OpenMP plus MPI can give you a very good scalability, no matter for single point, single thread, single node or multi-nodes, right? Because for single node, you need to use multi-threading. For multi-nodes, you should use MPI. And this is a very classic programming model. So I think I don't expect everyone to remember all the details for the class after maybe 1 or 2 years after you go to graduate school or you go to the industry or go to somewhere else. But OpenMP plus MPI, this is a very classic programming model. So after you choose or learn this class, someone asks you, what kind of the programming skill you are using in your class? So you should definitely know, okay, OpenMP plus MPI, right? So this is a very basic idea. And this is the project 5. And next week, we will start from the Cuda programming. So for Cuda programming, I will give you some idea what is a GPU architecture, right? It's totally different with a CPU. It has some similarity, but it's totally different with CPU architecture. And from the GPU architecture, I will give you some idea how you can write a good GPU program and using the Cuda programming model. Okay, and the final project would be based on the Cuda programming for the matrix multiplication. Okay, so I think that's it for today's lecture. Any question? So if you have any question, let's discuss. Feel free to unmute. Any question regarding the assignment, project, and OpenMP? No question? So I think some of your students may not be here, and I'm thinking about to have a fixed office hour with a Zoom. So I will post office hour for Zoom in the Blackboard later. And if you have any question, you can just join the Zoom for the office hour, right? Because I still think about some students may be shy to speak in the meeting room, right? So if you don't have any questions, that's it for today. And I will upload the OpenMP project online, and I will give you this project maybe 1.5 weeks to two weeks, a little bit long, but yeah, at least 1.5 weeks. Okay, I will upload the project now, and hopefully you can finish that on time. Okay, so if you don't have any questions, that's it for today. Yeah, thank you everyone for attending. Okay, take care. Mm-hmm.